Thanks for joining. So I'm Joe Spizak. I lead AI partnerships, AI ML partnerships for AWS. I hope everyone caught all of our announcements this morning in Andy's keynote. It was pretty exciting, and there's a lot there that we've been working on for a very long time. So I'll talk probably not so much about that, but more on the open source side in this talk. So I'm very excited and humbled, to be honest, to have my friend and colleague Peter Nordhaus from Facebook joining me here. And we're going to talk about scaling up vision models using Caffe2 on AWS. So we launched some really cool hardware this year in our GPU instances we'll talk about, as well as a lot of the work we're doing around open source. So this is really at that level we're going to be talking about in this session. So agenda-wise, I'll talk a little bit about what we've announced. Won't actually get into the details because I think everyone saw Andy's keynote. Hopefully you saw Andy's keynote. I know our team was all watching it. A little bit about deep learning and why GPUs matter and why we're excited about them. And then I'm going to hand it off to Peter, who's going to jump into Caffe2, how it's used at Facebook, and then really the work we've been doing together on optimizing Caffe2, not only for just distributed deep learning, but also on the AWS infrastructure for all of you developers to use. And then actually Peter has maybe a surprise for us. He has a demo of some work he's been working on that just actually came to light a few hours ago, so that'll be exciting. So we'll finish up with a demo and a little bit of call to action for everyone to take away here. So a little bit around the mission for AWS. Our goal is really to enable developers and data scientists, ML practitioners, application developers, essentially anyone at any level of expertise to be efficient and be able to use machine learning and really bring intelligence to their applications. It's a big meaty goal. We want to really drive this to every developer, every customer. We have more than 2 million customers now, and we want all of them to be using machine learning and AI. And that, of course, is challenging because not every customer has a team of data scientists or research scientists or ML practitioners that they can throw these really hairy problems to and say, go solve them. They maybe have application developers. They may have folks that are doing business intelligence. They may rely on partners. We don't know, but we're focused on really bringing it to everyone. And we do that in a number of ways. We focus on services. We launched a number of those this morning around translation, around NLP, video, speech recognition. We also launched the platform. It's called SageMaker, if anyone caught that. That was a big deal. We also focus on frameworks and infrastructure, and that's actually where we're going to focus more of our energy in the talk today. But you can see here the number of services, and this is pretty useless, but you can see at the top there the application services and platform services, everything that's new. And those are all really things we've been working on for the last year here, including updates to Mechanical Turk for deep learning and machine learning, adding video transcription, Comprehend, which is NLP, and SageMaker, which is kind of the crowning jewel of our AI launches or machine learning launches today. And that's really a hosted machine learning and data science platform. That was a really big deal. But really what we want to focus on today is, again, at this level, the lowest level, frameworks and hardware. I think Peter and I have both been in this space for a while, so this is actually where we get really excited. We're both in open source. And we'd love to see big parallel compute, training large nets. It's what gets us excited. So we're going to talk about that. And I'm going to cover just a few things that we've been working on in hardware as well as in open source and some recent announcements. So I think everyone saw the P3 announcement that came in October. The reason I bring this up is the foundation of a lot of the work that we've been doing with Facebook. At this point, it's kind of ridiculous. We're at a petaflop of performance in a single instance. So, I think our previous P2, if you look at the biggest one, it was under 100 teraflops. So it's 14x better than a P2. So incredible. We have now NVLink between GPUs. So for those that don't know, certainly communication between GPUs or compute devices is really key for deep learning, and Peter's going to talk more about that. But that really had a big jump from the P2, so 9x better than the P2, which is just using pretty much standard PCI Express. And of course, that has HBM memory as well. And you can see some of our launch partners like Airbnb, Toyota Research, and OpenAI. Second, the way we really harness performance and really get it out to developers is through our deep learning AMI. This is something that back when I was previously leading a product team, we developed this and really focused on the research scientist, the developer, frankly, anyone who wants to spin up an instance and have a deep learning and data science environment within a few minutes, really. So it's actually very cool. You can bring up this AMI. It has a number of different frameworks pre-installed along with NVIDIA drivers, libraries, Intel, MKL. Everything's pre-built, ready to go. It has Caffe2, it has TensorFlow, it has MXNet, Keras. You see some of the customers like Zendesk and SCDM who use it today. So this is really a foundation for anyone who really wants to just get started. And there's also a number of Jupyter notebooks that are actually present within the AMI, so you can actually just do an SSH tunnel into a Jupyter notebook, and you can start training nets basically within a matter of a few minutes. And then I also wanted to mention Onyx. So if folks haven't heard of Onyx, you should definitely check it out. So it stands for the Open Neural Network Exchange. And what we've seen between really Microsoft, Facebook, and Amazon is this desire, this yearning to bring research into production as quickly as possible. And from an Amazon perspective, we have thousands of researchers focused around Alexa, Prime Air, Amazon Go. Just the list kind of keeps going on and on and on what we're doing, personalization, recommendations. And we do that research in a number of parts of the world. They all use different frameworks, or they all use different tools. And so we see the same challenges that I think Microsoft and Facebook saw, in that there really needs to be some type of standardization with models. And so the promise of Onyx, which is ambitious, and we're very excited about it, is really to have a common format between these frameworks. So you can really interoperate between, say a PyTorch, which is a very nice research-centric framework, to a Caffe2 framework, which is more focused on production, which again, we'll talk about and how Facebook uses that, to MXNet, which, for example, Amazon uses at production scale today. And really being able to take research that was originally done in PyTorch, which is coming out very quickly, and get that into production basically like that. Like really this, even as it's being published, looking at trying to get it right into production and running on other frameworks which are built really for production scale. So we're excited about that, so definitely check that out. And with that, I'm going to pass it off to Peter. He's going to talk about Caffe2 and actually dive way deep into how they handle distributed deep learning and actually demo it at the end. So enjoy.
All right, thank you, Joe. Appreciate it. Hi, everybody. I'm Peter Nordhuis. I work at Facebook on Caffe2 and, more importantly, making Caffe2 fast. And I'll take you on a little journey to walk through the steps that you have to take to create a trainer, to distribute it, all the caveats, the potential bottlenecks, and that sort of thing. So with that, I'd first like to give you a little overview of Caffe2. So some of you may have heard of Caffe, the first Caffe. This came out in, I think, like 5 or 6 or 7 years ago or something like that. It was a grad student project by Yangxing Jia, who unfortunately wasn't able to make it here today. I know he was on the speaker list. He was the original author of Caffe2. It focused purely on computer vision applications, and it was really written to do one task really fast, and like that was it. So it was adopted very quickly since it came out at the kind of the start of the deep learning boom. Different companies took the original Caffe source code and made forks out of it. There were, like Intel made Intel Caffe, NVIDIA made NV-Caffe with all of their specific hardware optimizations in there. But it also caused like some fragmentation, right? So you had different flavors of Caffe that you would use on different hardware platforms. And if new features came up in any one of those, you wouldn't have those in the other ones. So that fragmentation wasn't that great. It is still a very popular framework, even though I wouldn't use it anymore because I think it's kind of like in maintenance mode. So moving on to Caffe2. So what is different about Caffe2? We have a full computational graph in Caffe2. So instead of dealing with like the tensors, the input types at a level that is very, very much suited for Caffe2, for computer vision applications, I'm sorry. In Caffe2, we don't really care what the inputs and outputs are. We create operators that take inputs and produce outputs. And off of that, we can create one big graph that we then execute. So it's no longer specific to computer vision applications, but you can do NLP tasks, you can do speech tasks or ranking tasks or whatever you want to do. You could even do linear regression with it if you really wanted to. Another big difference between Caffe and Caffe2 is that it has first-class distributed support, which is a big focus of today's talk. So I'll talk a lot about how the distributed support in Caffe2 works and why we built it the way we did. Another big feature that we're very excited about of Caffe2 is that it's inherently cross-platform. So instead of creating an environment where we would have these different forks come out by different vendors, Caffe2 is very modular, where you can have, let's say, a convolution operator, but you'll have one that works for Intel MCL, you'll have one that works for cuDNN, you'll have one that works for Eigen, and so forth, and so on and so forth. So as new hardware or new techniques to perform this computation come out, we can easily add them to Caffe2. The cross-platform nature is very important for Facebook specifically because we use Caffe2 both on our servers, but also in the Big Blue app. So what you saw in the movie, let me actually go back. Let's see if I can go back. Can I go back and forth? Yeah, so that video is an example of style transfer, which is something we execute on a mobile phone. If you have an iPhone like 6 or later, you can, and you have Facebook installed, you go to the camera and you can have all these effects. That is actually running Caffe2. So with that, I would say that Caffe2 is possibly the largest mobile deployment of deep learning frameworks out there. This is possible because it has this tiny core, right? This tiny core that if you compile it down to native code, it's maybe only like 100, 200 kilobytes. So it's very easy to ship this on phones and not have to worry about having to bring like gigantic interpreters or that type of stuff. That modularity is, I'll talk about that a little bit later. So if you want to actually build Caffe2 on these different platforms, we are very open with that. It's not like, oh, Facebook has its own built infrastructure for their phones and we can't get to use it. All of this stuff is open source. So if you go into the Caffe2 repository, you'll see our CMake build system, which supports a variety of platforms. So if you want to compile for iOS, for Android, even for the NVIDIA Tegras, for the Raspberries, then you'll be able to do so. And here's a couple of examples of the tasks, in this case, computer vision tasks where we use Caffe2. On the left-hand side, you see a computer vision task called image segmentation and identification. Instead of taking a single image and saying, hey, this is a beach. That was the classical computer vision classification task. Instead, research has advanced so much that we can now say, well, okay, what are the different objects that we recognize in an image, and how can we classify those individual objects? The next step yet, you see on the right-hand side, which is where we take that segmented information and can do something called pose estimation. All of these tasks are powered by Caffe2. The modularity, I hinted towards it earlier a little bit, is very, very powerful. So going back to that convolution operation, I was talking about cuDNN and Intel MCL. There's more of them, of course. Right? There's an NPAC, which contains a lot of like low-level assembly optimizations for x86, 64, and ARM. And of course, you can plug in custom code. Metal is the iOS backend for performing neural network primitives. If I say that correctly, I think I do. It's an API that gives you the same level of granularity as, for example, like a cuDNN. So that's where you tap in if you're running on iOS. Now, the input and output doesn't change, right? The numerics of the operation don't change. It's just that on a particular hardware platform, you'll be able to execute it faster than on others. Okay, so I kind of covered this already, but yet another one, Snapdragon. Yeah, on the Qualcomm phones, we also have the Snapdragon library. So I already forgot about 2 of them here, but we already covered like 7 different backends that you could use for a single operation, and all of this is embedded in the same small Caffe2 core. So there's no longer a need to have a different fork for different backends. Extending Caffe2 yourself, if you want to, is also fairly easy. We have a directory in the Caffe2 repository called contrib, where we hold a number of extensions that can be compiled optionally with Caffe2 target. One example of that is actually the operators that we use for distributed training. But another example is, for example, the Teensney. Oh, there was a little animation in there, but I'm okay without it. The Teensney operation, for example, allows you to visualize a higher dimensional space in a lower dimensional space, which can be very helpful to visually detect minima and stuff like that. Adding something like that is as simple as creating a new C++ class that inherits from the base operator class and registering it. If you compile that down to a shared library and you load that at runtime, you have access to it, and it can be part of that computation graph just as any other operator that you're already using. So with kind of the introduction and the skeleton or the framework out of the way, I want to take you on a tour here, defining how you actually go about defining a model in Caffe2 and run it and subsequently distribute it. So in Caffe, a model is the container for all operations. So this is kind of like you can think of it as a list. And in this list, you're going to say, hey, I'm going to have an operator that, for example, does image input, and it's going to produce an output, 2 outputs, which is going to be, in the case of a computer vision task, an image or a set of images and a label or a set of labels saying, oh, this is a beach, this is a car, this is a truck, that type of stuff. This series of labels or this series of operators can be defined sequentially, and because we use the same symbols for outputs and subsequently inputs, we can distill that list of operators into a graph where we can then parallelize at will without sacrificing correctness. So in this example, we're going to build a ResNet 50 model. The model helper is going to be the container for all the operators, and it will also convert to the protobuf. So the protobuf, the protobuffers are a Google standard for defining structure. Like there's an IDL you define. These are structs with types and fields and that type of stuff. That's what a Caffe2 model can be serialized into, and you can take that protobuf and then ship it someplace else to run it. So this is how you serialize a model, both the definition of a model and the weights of a model. The arc scope in this case is the order for the tensors that we're going to be using. So there's 2 different modes. Actually, you can have any permutation of this order, but 2 commonly used orders are either NCHW or NHWC. The N stands for the number of examples in a batch. So whenever you're training, you're going to train on like a whole batch of data at once, because that works well with your SIMD units and your massively parallel GPUs and that type of thing. The C stands for the number of, or for the channels in an RGB image. So in this case, it can stand for RGB, BGR, some kind of channeling. You could also consider a model where you also train on like an alpha channel, although that's not really common. Then we also have the H and the W channels, which stand for height and width. We define the arc scope at the model level helper so that further down we don't have to repeat ourselves all the time. So the arc scope is going to be propagated to all the operators that we define later on this model helper. For the next one, like the next example that we see here is defining the image input operation, which we define through what's called the Brew API. In Caffe2, this is all defined under a helper subdirectory, which contains a large number of files with helpers to define our operators. You can imagine that there's a large number of configurable arguments to different operators, and you don't want to define all those operators all the time because you'd be repeating yourself and it becomes very inconvenient. And for that reason, we added this Brew API where a lot of that is abstracted for you and you only get to define the things that you care about, and it uses sensible defaults for everything else. In this case, the Brew API is also always stateless, so it's just a static function. It takes the model that you operate on, it takes inputs, one or more inputs. In this case, we give it a reader input, which is an object that can read data from disk and seek in that larger data set. Conceptually, you can think of this as the place where the images come from and are either like decoded, JPEG decoded, or something like that. Then we have a series of outputs, in this case data and a label. Data will hold a tensor of the type NCHW, right? So we'll have n being equal to the batch size in this case, let's say 32. So we'll have 32 images with 3 channels of 224 by 224, because that's the crop that we tell the image input operator to take out of that larger image. There's a much larger set of image augmentation operations that the image input op can perform, but I leave those out for brevity here. So when we then go and define a model, we don't have to think about like, hey, what kind of convolutions and what kind of fully connected layers shall I include every time? That's what research is for, right? So research produces every now and then a model that is kind of the current state of the art, and we get to reuse them as we see fit, and typically use either the final output stages or some of the later stages in the model as inputs to our own models. So in this case, we can say, hey, we want to create a ResNet model, and conveniently enough, Caffe provides a bunch of helper functions again to define these canonical models on a model object that you define. So in this case, the ResNet helper takes, again, like the Brew API, the model as input. It takes another argument here, in this case, the data. Like, what is the data that's coming in? Well, it was produced by the image input op earlier, and the label, as well as a number of labels. So in the case of the ImageNet 1K classification challenge, we're going to have 1,000 labels. And this is like an output vector of size 1,000, right? If an image is a beach, then at n equals 0, you'll have an image of a beach. And then at n equals 0 of the labels, you'll have a 1 at the position that represents a beach, with everything else being 0. The model definition helper also returns a loss function that compares the actual output of the network with the expected output. Like you know what class of image this is, so we can compare the two and then compute a gradient with respect to that loss, which we then use to update the model in the next step. So the subsequent step here is to take those gradients and take a fraction of those, compute like some moving average, that type of thing, and update the weights of the model to iteratively get to the best minimum and get to the best accuracy model. All right. So with that model built, we haven't trained anything yet, of course. So let's take a quick look at the main training loop, what that typically would look like. You can imagine that it's more complex than this, but this is the basic skeleton of it, and it would work. So we can't just train once over our entire input set, because we only get to see our data once, and that's not enough to actually learn the classes of that problem. We have to go over it typically like 90, 100, 110, 120 times. And that's what num epochs in this case is. So we create one big loop where we train, let's say, 90 times. For every epoch, what we call it, we have to run the network enough to see the entire data set. So in this case, we take the size, the epoch size that we use for training, which in the case of ImageNet 1K is 1.2 million images that we train on. We divide it over the batch size, Recall that's the n that we specified before, the batch size, the number of images that we train on in a single iteration, and get the number of iterations we have to run in order to see the entire data set in a single epoch. Now, if we would leave it at that, we would be good. We could stop right there and say, well, we'll just run 90 times, and it produces a model, and then we evaluate its accuracy, and then choose whether we like it or not. However, in practice, it is wise, or yeah, it's probably wise to also, after each epoch, test what the accuracy of the network is. And this is how you get your training curves, right? If you've read some literature about model architecture, then you've seen those training curves that start high and gradually go to a lower spot, ending up at like the top 1 accuracy of, let's say, 25%, 20%, something like that. In order to do that, we run the model again, but on a separate model. In this test model, we don't care about computing a gradient because we only use it in a forward pass. We use it we compute the forward pass, and after that we check, hey, was the model right or not? If it was, then we say it's accurate. If it wasn't, then it's inaccurate. We average those accurate and inaccurate classifications over the entire test epoch size, which, I mean, it's up to you how much you want to do this. This also costs some time, some computation, so you could either choose it to be like 10,000 or 50,000 or 100,000, it doesn't really matter. But you can use this to compute your accuracy. Now, so far, what I've talked about is just like how do you define a model and how do you define a trainer, but it doesn't talk anything yet about actually scaling it up. This is 100% iterative. And sure, Caffe2 will exploit parallelism where it can, right? If you visualize a graph, it's not going to be a linear sequence of operations that you execute. There's going to be branching in there. For example, in the backwards pass, if you compute the gradient of the next level up and the next level up and the next level up, you can separately perform your weight updates, right? So all of that branching is exploited by Caffe2 in the form of parallelism and multiple threads running the operators that can be run on that graph. So let's talk a little bit more about scaling up and what, well, some caveats that come into play there. So the first step is to actually talk about the type of scaling, what we're going to be doing. There's generally 2 classes, weak scaling and strong scaling. The batch size that I talked about before in a single thread of execution, like let's say that's 32. If you talk about strong scaling, you can use like 8 GPUs, but you would also divide that batch size by 8. So you would end up only using a batch of 4 per GPU. Right? And if you go to 32 GPUs, you use a batch of 1. And after that, you can't do strong scaling anymore because that's your batch size. That's your global batch size. Instead, if we talk about weak scaling, we just like throw more compute at the problem. We say every worker will use the same batch size, so the more workers we use, the larger the batch size becomes. Right? There's no numerical equivalency anymore between using 1 worker or 2 or 8 or whatever. The batch size grows, and that's how we get our throughput. On a related note, there's also data versus model parallelism. When we talk about data parallelism, we say, well, we'll just throw more data, run through data more through the model, and at the same time versus individual operators being run by multiple nodes. That would induce way too much communication. So out of these modes, we focus at Facebook mostly about the fourth one, where we use multiple machines and each machine uses multiple GPUs. To illustrate that a little bit more, here's a curve describing what the GPU throughput, how the GPU throughput degrades with a shrinking batch size. So if you look at the optimal batch size here at the very tail end of the curve, 64, you get a throughput of roughly 390 images per second. That's great. So you say, well, we can apply strong scaling here if we like double the number of workers. Sure, but that means that we go to a batch size of 32 per node, and we only see performance of 350 per second. Now, for your application, that might be fine. You might say, well, okay, I can take that hit, that little hit of inefficiency, as long as the numeric stay the same. But if you apply that step again and you end up at 300, and again and you end up at 250, it starts to degrade and you stop being able to scale further. So this is why we like weak scaling much better than strong scaling. Just it's easier to do and you can scale it much further. You don't hit that wall as quickly. So in order to parallelize a model, we have a helper in Caffe2. It doesn't require you to define your model 8 times and do all of the synchronization yourself. We abstract that in Caffe2 in a helper function, which we call the data parallel model. It takes as input a train model, which again is the output of like the model helper that I showed before. And instead of defining the model once, we extract the process of defining the model into a lambda that we end up calling from this parallelize function. So what will happen is the parallelize function knows, hey, I want to create 8 instances of this model because I have 8 GPUs. It will call that a create model operation 8 times, but with different scopes. So it will say, well, I'll create one model where all the inputs live on GPU 0. I'll create another one on GPU 1, and so on and so forth. That's not the end of it, though. Like if you would just instantiate the model 8 times and run with that, and like you're okay with that, you end up with 8 different models. Like there needs to be communication between them in order to train jointly. So this is inserted by the parallelize function in the data parallel model automatically. It's not something you have to take care of yourself. And what happens is that before applying the weight updates to the models in the backwards pass, it will average them across all the participating devices. And these devices can be either like single GPUs or GPUs in a machine, but they can also be GPUs in a machine and across machines, which is what we end up doing for multi-machine training. So to illustrate the problem with this communication step, let's look at a little diagram. So if we run through a model, you can imagine that we have layer 1, 2, 3, we run the forward pass. In reverse order, we run the backwards pass. We have layer 3 backward, 2 backward, 1 backward, and then we apply the updates. Right? We get the gradients from the backwards pass, and we apply the updates according to those gradients. Now, if we parallelize, we insert an extra step. We have to synchronize those gradients across all the participants before doing the updates, otherwise we wouldn't end up training jointly. And this adds execution time. However, when you think back of the graph that I talked about, the compute graph, there's no data dependency between some of these. So what we can actually do is, as soon as we computed the gradients of the 3rd layer, we can reduce and update in parallel with computing the gradients of the 2nd layer. And this is how we exploit scaling up the process of training a model without taking a big hit on the scaling linearity. So depending on the performance of these synchronization operators, we can scale with either near linear scaling efficiency, or worse than that, let's say if your synchronization is very slow. This is also where the point that Joe made earlier about NVLink on the P3 instances comes in. With NVLink, you'll be able to synchronize faster, so this synchronization step is going to insert less of a delay in your overall training time. Another problem that we see with achieving this scalability is that if you have a box with 8 GPUs in it, you'll also have to saturate all those 8 GPUs. And if these GPUs become faster and faster, it puts more and more strain on the CPU to actually produce all those inputs. And think about it. Like if we have a P3 16 large and we do like 2,600 images per second, or like let's say even 2,000, and you have to do JPEG decode, crops, and image augmentation for all of those, that puts a lot of stress on the processor. And this is a kind of a well-understood challenge, and there's probably will be a time when we have to offload some of these tasks elsewhere just because the GPU silicon will become too fast. If we want to parallelize for multi-machine, not just focus on a single node, what do we do in Caffe2? Well, it's actually not that hard. We can define a dictionary where we say, well, there's going to be 4 participants. I am number 0. We'll use a TCP transport, and we have to have some key value store on the side to perform a service discovery. We pass that to the parallelize function, and that's it. So the parallelize function will take care of all of the steps needed to actually have the machines find each other and then start communicating. The operations that it will insert in the operator graph, instead of only performing reduction locally, they'll perform reduction across machines. So the scheduling aspect there, in Caffe2, we don't take a big bet on like saying, hey, we want to use this scheduler or that scheduler. We don't really care. As long as you can feed Caffe2 with the right information and provide it the right means for initial communication, then we're fine with it. So it can be either like, I guess, Joe, the container service is now outdated. We now have EKS, and we have all these other fancy things. So who knows, maybe if they at some point support GPU instances, we'll be able to use that. If you have an HPC cluster, like a traditional supercomputer, you might end up using Slurm and MPI. Or, as I'll demo in a little bit, you can also just be a person typing SSH commands, and that's fine as well. The rendezvous step is where different machines will have to find each other in order to communicate. So this is not a standard like master worker type architecture where you have one node and it takes all the updates and then broadcasts them back out to everybody, because that would put too much of a bottleneck on that single machine. Instead, this is an all-to-all or it can be an all-to-all communication pattern, but we don't take any particular node that participates. It's not going to be special. So we separate finding all the nodes from doing the actual synchronization. This step we call rendezvous, and you can use any key value store or shared file system to apply this. And what ends up happening is roughly the following. If we start a trainer, assume like left is one machine, right is the other machine. We start a machine on the left side, we say ID is 0. On the right side, ID is 1. The left side will set an address like a TCP address of a socket it opened itself and is listening on, at a predefined key. The other side does the same thing. And because they know I am 0 and I'm 1, and there's going to be 2 total, it can compute the address that the other nodes will set their keys at, and it can wait for them. After everybody has set their addresses that they listen on, they can massively connect to one another. And since these are all going to be listening sockets, we do a simple byte compare on the socket address. And if we're smaller, we close and connect to the other one. And if we're larger, we call an accept and wait for the other person to close. After that, we have a connected TCP socket, and we can communicate whatever we want over there. So this reduction step, this synchronization step, where we have to take the gradients of these layers and synchronize them, is also called an L-reduce, and it happens in 3 stages. First step is that we have to reduce from all the GPU buffers. And recall, if we have a box with 8 GPUs, we'll have 8 different gradients. We have to reduce all of them into a single buffer that represents the buffer for that machine. Subsequently, we run an L-reduce across the machines to get the final reduced gradient. And after that, since we still have to apply the updates locally on those GPUs, we do a broadcast within the machine from system memory back to the GPUs. We end up doing a single one of these operations per layer, so per every, or actually per buffer per layer. And the runtime will depend on the size of this buffer, but also the networking speed. You can imagine having, let's say, a model that's a gigabyte in size, 250 million parameters, float 32. Then if you only have a gigabit of networking bandwidth, it's going to take you at least, like theoretical minimum, 1 or 10 seconds to communicate all of that data. If your GPU spent only half a second to compute the forward and backwards pass, you're going to be spending 20 times as much time waiting on the network for that synchronization to complete, and you won't be doing efficient scaling. So in that case, I would encourage the operator of that system to use like 25 gigabits or maybe 40 gigabits of networking and not have that bottleneck. Looking at the parameter size distribution, so every one of these layers will have its inputs and weights. We see on the left side everything that's smaller than 4 kilobytes. So a lot of them, actually the majority is smaller than 4K, and these reduction operations will be very much bound by the latency we have between machines. Right? It doesn't take a whole lot of time to send a 4 kilobyte packet, but if you aggregate the total amount of time that you send stuff around, you're going to be waiting on the latency is going to be the dominant factor. Whereas if we move to the right-hand side, we have a couple very large weights where the bandwidth is going to be the dominating factor. So to illustrate this a little bit more, we can express the scaling efficiency that we get as the time it takes to do a forward pass and a backward pass, and divide it over the time it takes for a forward pass plus the maximum of a backwards pass, and the time it takes to reduce all your parameters given your network bandwidth. And if you look at this curve, it can become a problem fairly quickly if your model is large. So taking the network speed into account is very important there. Some observations for multi-machine. We've been doing this for a while now at Facebook, and we've seen like everything that can happen. If you have a single slow machine, whatever it's doing, it can be doing like some management task on the side. If it's slowing down that trainer a little bit, it will slow down the entire collective, given that all of these operations are synchronous, right? They have to wait for each other. So if you have a single slow machine, it slows everybody down. It only scales well if we're on the left-hand side of that efficiency curve. If the time it takes to reduce these gradients is lower than the time it takes to do the backward pass. Otherwise, we start waiting on the network, and our efficiency goes way, way down. Applying weak scaling can be done to extremes, and it has been done to extremes. The current state of the art was a paper from Preferred Networks in Japan, and they scaled it to 32,000 on a set of 1,000 GPUs. At Facebook, we did it up to 8,000 on a set of 256 GPUs earlier this year, which inspired this work. And it's not a free lunch. Like if you keep scaling this up, let's assume you have 2,000 GPUs at your disposal, and you say, well, we'll use a batch size of 64K. Well, that doesn't mean that the accuracy is going to be equivalent after training that model. So it's not free. Like it does still require tuning to get to this way higher scale. All right. Talking about AWS a little bit. So far, this has been generic Caffe2, and you can run this on like machines under your desk, a supercomputer, right? It doesn't matter. Like as long as you have a network cable between them, you can run this and you're good. Now, luckily, AWS gives us the virtual equivalent of that, right? You can just launch a bunch of machines, and as long as they're in the same VPC, they can talk to each other. So that's great. What Joe talked about before a little bit. Amazon publishes the Deep Learning AMI, which contains all of these different frameworks, including Caffe2, and including the latest CUDA and cuDNN libraries from NVIDIA. The rendezvous step that we need to perform to do distributed training in Caffe2 can be performed, that task can be performed by Amazon Elasticache. So Elasticache can provision a Redis instance for you that we can then pass to all of the trainers that are participating, and they can perform service discovery there. And VPC for private network, this is kind of implied, I guess. We need a total access between all these machines. So having firewalls in between is just a big burden, effectively, because we'd have to go and open a ton of ports from everybody to everybody. So ideally, just use VPC and have a open access to everybody. Optionally, I've played with this a little bit, is using EFS for storing checkpoints. With EFS, you get a single mount point, an NFS mount point that can be shared between different machines, and that's perfect for storing, let's say, like checkpoints. Optionally, also input like training data and that type of stuff. So you can use Caffe2 directly from the AMI. This is going to be the stable version of Caffe2, which is at time of as of now is 0.8.1. We also publish Docker images for Caffe2, both the stable version, but also the nightly version. So if you want to have the latest and greatest, then you can go on Docker Hub and pull down the latest Caffe2 image and use NVIDIA Docker for execution on these GPU instances. One last thing on running Caffe2 on AWS. If you have a large data set that you're working with, you still have to bring that onto the machines. And that can be non-trivial. Like I downloaded a large data set off of S3 just today, and I got a maximum throughput of roughly 150 megabytes, which is decent, I guess. I mean, that's pretty great. But if you're talking about 140 gigabytes, it's going to take 20 minutes. And if you plan on training for 20 minutes, you're going to have a machine that sits idle for 20 minutes while it's downloading all the data, and then 20 minutes for training. So there's more work to do there. There's more opportunity there as well to improve that situation. All right. So with that, I want to show you a little demo of what this looks like. Let's see if it still works. So what I did was provision some P3 instances this morning. Let's actually bring it up a little bit. Okay, full to 0. So I provisioned some P3 instances, the large ones. You have the single GPU ones, and then you have the 8 GPU ones. These are the 8 GPU ones. And I can show you by running NVIDIA SMI, and that's great. We see 8 Tesla V100s. Each of them have 16 gigabytes of memory. And to run a trainer, what I did was use the nightly build of Caffe2 and create a little script so that I can kind of walk you through all the stuff that we have to specify and kind of fill in the blanks that I didn't cover yet. So in this case, we're going to use the NVIDIA runtime. This is a Docker wrapper that is built and maintained by NVIDIA, whose task it is to plug through the NVIDIA driver libraries into a container. Otherwise, you don't have access to CUDA and the NVIDIA driver and can't use GPU workloads. We have to pass through the network as well. By default, Docker runs with network isolation. And in this case, we want these machines to talk to each other. So we bypass the network isolation and just inherit the networking namespace of the host. So we can use the host's networking interface. We use the Caffe2 Docker image off of master. And we run an example here. And this is the ResNet 50 trainer, or a ResNet 50 trainer. I think if you would take all the code that I talked about today and put that in a file, you'd have roughly the equivalent of what's in this one. But it also takes some arguments. It has some argument parsing and some logging and that type of stuff. We specify to use 8 GPUs, total batch size of this run of 512. So we'll end up, if you recall that efficiency graph of throughput over batch size, we'll end up all the way on the right end of that graph with 64 images per second, or 64 images per batch per GPU. We specify the image size. We specify a workspace limit. In this case, because I wasn't able to get the training data on these machines in time, the training data is null. So we're not going to see a bottleneck based off of reading and decoding training data. And the last 4 are unused for a single run, but we'll see it later for a multi-machine run. So if I just run this, Then it will start a Docker container. It will find the 8 GPUs. It will set an initial parameter sink. Like if you start training and you initialize that with random values, you want to make sure all the GPUs have the same random values. Otherwise, you start with a disadvantage. The memmonger in this case is a graph transformation technique that Caffe2 uses to decrease the memory usage. And then whenever we see this message where it says starting epoch, it will start all the operators. All the memory is allocated lazily, however. So the first step after starting epoch in this case takes longer because the process ends up allocating roughly 80 gigabytes of GPU memory. And that's not free. I mean, it takes some time. So after warming up a little bit and everything's done, well, we're processing roughly 2,100 images per second. And you can compare this to the previous generation, which was NVIDIA Pascals, which do roughly 40% less of this. And then the generation before that, which would do another 40% of that. So the improvements that have been made on the performance side over the past couple of years are pretty intense. All right, so let me just quit this because we're training on bogus data. This is not going to be, well, giving us a nice model to work with. So instead, let's take a quick look at what happens if we run this on 2 machines. So I have the same instance 0 here, but I also have an instance 1. I guess it kills connections after a while. And let's see. So we'll call run. Do I have another command in here somewhere? No. Run. And we'll specify that we're going to run with two instances. And I'm going to be number 0. And we're going to specify a run ID so that they can find each other. Run ID is kind of like a token. You can think of it as a token. So 1, 2, 3, 4, 5, 6, 7, 8. All right. Here, we're going to run the exact same command. And notice this is a different machine from the first one. Num shards 2, shard ID 1. Specify the same run ID. 1, 2, 3, 4, 5, 6, 7, 8. And let's see if I made any typos here. But what happens now is at the initialization step, we'll do that same that rendezvous step, right? So both machines will set a bunch of keys which hold TCP addresses of sockets that they're listening on. And after they find the addresses of their peers, they'll go on and connect to each other. All right, there's some Docker-related thing there, but we can ignore it. Right now, both machines are doing all of the initialization again, so they're doing all of that memory allocation, that's like roughly 80 gigabytes. I see that if we run this, we roughly end up allocating 10 gigabytes of memory per GPU with a batch size of 64. All right. So what's happening? Well, we see a little bit higher throughput, and that's good because that's what we want, right? We want, if we use 2 machines and we spend twice as much money, we want to see, like, ideally see twice the throughput. And in this case, we do, right? We saw 2100 before. We actually get a little superlinear improvement here, like it's not 4200, but actually 4400. This slight difference has to do with the interleaving of operations that ends up being different if you're only running on a single machine versus on multiple machines. You can imagine that the updates will be staggered a little bit wider, which causes less contention on the GPU and ends up with a little sublinear bonus here. So with that, I've shown you that I'm not selling snake oil. This is real stuff. It works. Right? We get awesome performance. We get awesome performance on AWS out of the box. And I think with that, I'd like to hand it back over to Joe for a little bit.
Cool. Yeah, I think we're going to wrap up quick because we're running out of time. We can take a few questions if folks want to start lining up at the microphones there. We can switch back to the slides. Cool. So I think we're, again, out of time, but I think the key takeaways here, you can You can see we support Caffe2. We support a number of different frameworks. So we really support Caffe2, though, working closely with Facebook. You can also get started quickly at Amazon AI/AMI, so check that out. It supports Caffe2, PyTorch, a number of other frameworks, as well as you can go to Caffe2.ai and also see a lot of the work that Peter's been working on there and get started there with a lot of code examples. And so since we're almost out of time, I want to take a couple of questions. So why don't we start right here?
Thanks, Peter, for the awesome presentation. The question I have is, do you actually need a parameter server or something equivalent in order to do the gradient calculation from all the different machines?
Yeah, so this is kind of a philosophical thing, almost, I guess. In this case, where we have all machines doing the same reduction, you don't. I think that what I've seen so far, parameter servers are great if the size of those parameters becomes too big, right? And you don't have to update the whole thing at once. Then it's great to have a parameter server. In this case, you could also choose to use it, but it would have vastly different performance characteristics, which is why for the distributed support from the Caffe2 data parallel model helpers is doing all of the synchronization without a parameter server. So it's like all-to-all or like tree-based or ring-based type communication.
So still there needs to be some synchronization happening across all the different machines in terms of making sure that every one of those machines has actually communicated the information back.
So that's going to be kind of implied by the operator start and end. So we capture the synchronization step in a single operator. So from the Caffe graphs perspective, we start with an input that is unsynchronized, and once it produces the output, everything is synchronized.
Okay, cool. Thank you.
Let's take one more question. I think we're out of time, and we can hang out here for a few minutes and chat as well. So why don't we take one more over here?
So I'm an experienced software engineer, and I want to get started with machine learning. Is Caffe2 a good choice to start playing around with? And if so, besides sort of the tools Amazon has been provided, what about tutorials and references, initial sort of tasks to tackle? How do I get started?
Yeah, I think there's for Caffe2 we have a couple of tutorials out there which are like IPython notebooks that you can load up on one of these instances. You have to allocate a GPU instance on Amazon, start the notebook, and then kind of walk through the tutorials. Besides Caffe2, kind of part of the larger Facebook family of machine learning tooling, I also recommend giving PyTorch a look. That's really great, and kind of the whole idea behind Onyx is that you can take either framework and productionize it in just the facet that's available. So it doesn't really matter which tool you use for getting started, for kicking the tires, for figuring out how all of this stuff works. Once you want to productionize it, you can use the fastest runtime out there. So I think take a look at the Caffe2 tutorials. Also take a look at the PyTorch tutorials, and
I think one last thing. I think check out SageMaker. You can actually use the plugging Amazon service here, but you can actually take the Docker container that is provided from Caffe2 and actually bring that to SageMaker. So you really choose your framework that way, and that actually, the brilliance of the distributed deep learning work that Peter's been doing with the other Facebook folks is amazing. But if you don't want to go through everything that Peter goes through to distribute, that's actually taken care of for you with SageMaker. And you can actually focus and actually try out Jupyter Notebooks that way, start actually playing with real problems, start importing data sets, and really get started quickly in a distributed manner. So that might be a good place to start as well.
Awesome, thanks.